Hello pre-calc people. So I want to keep this short, so it's going to be a very simplistic introduction to limits, and we're going to be looking at them from several perspectives. One is going to be graphical, numerical, and algebraic. And we're going to start off with the basic definition of a limit, that as you approach a certain value, x value, your input, that corresponds to a certain output. Now the way I like to describe this is, let's say you're constructing, you're manufacturing pipes, and you know that your pipe has to fit into another pipe, and you happen to know how much air there is allowed around your limit, around your pipe, so that the two pipes fit together. Knowing that amount of air that is allowed, you can work backwards to control the input. And that's kind of what we're going to be doing algebraically. Knowing what our limit is and the interval around that limit, we can then control the interval around our input that keeps whatever value we choose within our limit. Okay? It's hard to describe this through video, but we're going to do the best we can. So we're going to go back down here to our first kind of algebraically, numerically example. So we look at this equation here, and it asks us, what is f of 3? So we look at this, and you notice that there is a hole in our graph. So f of 3 is not actually defined at that point. So we would say, what is f of 3? Well, f of 3 does not exist. There's a hole there. And so we can see that there's a hole. But if we go through and simplify, so down here we have the equation that defines this graph. So to simplify that, remember we can do our synthetic division. So we have 3 is going to go into the coefficients. So 1, -5, 8, -6. So a little review on how to do synthetic. Bring down the 1. 3 times 1 is 3. Add those, you get a -2. That gives us a -6. Add that, you get 2. So remainder of 0. So this reduces your polynomial by 1 power. So this becomes x squared minus 2x plus 2, with of course a hole at 3. So now I can actually go through and figure out what that corresponding value would be. And I can do that by taking the limit as x approaches 3 of our new function, our simplified function, where 3 is not a problem. And we do that by actually plugging 3 in. So when I plug in 3, I get 9 minus 6 plus 2, which is going to equal 5. So we find out that the limit as x approaches 3 is 5. In other words, it's kind of like approaching somebody's house. You and your friend are both going to a friend's house. It doesn't matter whether they're home or not. You're still approaching the same house, and that house happens to live at the y-coordinate of 5. All right? So that's what we found. The limit as x approaches 3 is 5. Okay. Now, what we want to do is we want to control the interval around 5. So we want to find the biggest possible interval about c equals 3, so around this input, so that we keep our f of x within 0.1. So here's the error that we're trying to control. So we know we can go up to 5.1 and we can go down to 4.9, because that is within 0.1 of our limit 5. And we want to find what would be the corresponding, so if we carry this through, what would be the corresponding input that keeps us within that interval. So the way we do that is we set our f of x equal to 5.1, and we're going to use the simplified version. And when I do that, and then I'm down here, I'm going to have 4.9 equals x squared minus 2x plus 2. And so notice we have two quadratics. So in both cases, we're going to set them equal to 0. So I have x squared minus 2x. And then for the 5.1, this becomes minus 3.1. And then we use our quad program on both of these. So this one will be x squared minus 2x minus 2.9. And what the quad program gives us is two different values. So it's going to give us x equals, for the 3.1, I've got 3.025, and it also gives us negative 1.025. So this second one, since it's not around 3, we're trying to find an interval around 3, we throw out the other answer. And for the 2.91, when we do the quad program, it gives us x equals 2.975 or negative 0.975. And again, we throw out the interval that is not around what we care about, which is 3. So we have found an interval around 3, so between 2.975 and 3.025. If I can keep my values within that interval around 3, then my output will always be within 0.1 of my limit. So we're going to put down here the interval is going to be between 2.975 less than or equal to my C value and 3.025. So then it says choose a value of x within the interval you found to show that it really is within 0.1. So choosing something, just something within that, something obvious, I'm going to choose 2.99. You cannot choose actually 3. We have to choose something, anything other. So if I choose 2.99 and test it, what I'm going to do is I'm going to plug it into my x squared minus 2x plus 2. So that gives me 2.99 squared minus 2 times 2.99 plus 2, which gives me 4.9601, and that is within 0.01 of my limit, which equals 5. So that would show that we can choose that any number within that interval will keep us within our acceptable output, which is sort of represents our error that is acceptable. And then I was going to go through and show how you could also use the table feature on your grapher to look at those values as well. But that's kind of hard to do through a video, so you're going to have to take my word for it. So here, this top example is where I want you to actually go through the process. So we're given the function y equals 2 of x. And so this is an exponential, and we know that here is our input where the C value is going to equal 1. And if I plug in 2 to the 1, we know our output will be 2. So they're calling that h of 1. And we want to find a value that keeps it within 0.1. So we're going to go up to 2.1 and down to 1.9 again. And so that's going to be a really close interval around here. And we want to find the corresponding interval around 1 that keeps our output within 0.1 of our limit. So just like before, we want to go through and, sorry, just erasing some of my random marks. We want to set 2.1 equal to our function f of x and go through and solve. In this case, you're going to have to use logs. So log of 2.1 equals x times log 2. So taking the log of both sides brings that exponent down. And then divide both sides by log 2. And that's going to give us x equals 1.070. And then we will do it on the other side. So 1.9 equals 2 to the x. So we have log of 1.9 divided by log 2. That's also going to equal our x. So that gives us x equals 0.926. So in this case, we have 0.926 on this side, 1.070, and that would be the interval. And if I want to double check that this truly is the interval, I can choose a value within that range. Again, I'm going to choose x equals 0.99, something close to 1. And 2 to the 0.99 is 1.986, which is within 0.1 of our limit, which equals 2. Okay, so that's looking at it numerically and algebraically, trying to find that interval. Now what we're going to do is look at the concept of a limit graphically. So when you're looking at a limit graphically, this is going to be really hard because I do a lot of hand motions when I'm teaching this, so you're just going to have to bear with me. Here we have the concept of you're approaching a graph. If you see the little plus sign here, that means you're approaching from the right, from the positive side, and you want to know what your actual graph, what y value your graph is approaching. If you see a negative, that means you're approaching from the left, from the negative side, and we want to know, so this is approaching from the right, this is approaching from the left, and that would tell you which y value your graph is approaching from that side. And if you see nothing, it means you're approaching from both sides at the same time. If those two limits don't exist, if your fingers don't go to the same place, then there is no limit. In other words, the two one-sided limits have to be the same for the overall limit to exist. So you can have a one-sided limit. It doesn't mean you have a two-sided limit. Okay, the two-sided limit has to agree in both the right and the left. Let's look at how this works graphically. So here we have this graph with all kinds of different things happening. And the first question is, what is the limit as x approaches 3? So remember that your answer here is always going to be a y value. So the input is actually the limit. What is x approaching? So x is approaching 3. So we find 3 and we follow it up, and the corresponding y value is 5. No problem there. That's all good. Okay. So then we go down to what is the limit as x approaches 1. So here is 1. So as I go up to the actual graph. So I'm looking at what is the graph approaching from both sides. This is what we talked about before. It doesn't matter, that whole doesn't matter whether, it's kind of like somebody's house. It doesn't matter whether they're home or not. You're still from both sides approaching the same place. So the limit here is 2. The actual value of f of 1 is 1. That's the dot down here. Okay, that's kind of like saying, yeah, we went to your house, but you weren't home. You were at the house next door. That's okay. We were still both approaching your house from both sides. Okay? Now we're doing the limit as x approaches 2. This has a negative. That means I'm approaching 2. This is getting really busy looking, so I'm going to erase this for a sec. We are approaching 2 from the left. So here is approaching 2 from the, sort of from the negative side. We're approaching from the left with your left hand. So notice the corresponding y value would be 3. If I'm approaching 2 from the right, I'm approaching the x value that is 2. My corresponding y value is 4. I have 2 different limits. If I were doing my hands at the same time from both sides, they're not going to the same place. So that means the overall limit without a plus or a minus does not exist. You're not going to the same place. You don't have one limit. Okay, so now we go down to the limit as x approaches 4, and there's no problem there. The corresponding y value would be 3. And then last one is as x approaches y. Notice that at 5, you have, basically there's an asymptote going here. So you could give 2 possible answers. You could say positive infinity, which talks about the behavior of the graph. Both graphs are going off to positive infinity, or you could say the limit does not exist. You will never have both on a multiple choice test. They both mean the same thing, does not exist. There is no limit. It's growing without bound. But if I want to talk about the behavior of the graph, I could say it's going to positive infinity. You're always safe by just saying it does not exist. Okay? All right. So that's finding a limit graphically. Now, we want to start looking at finding them algebraically. So this first one, we're going to consider the graph of square root of x over x. We're going to be giving you a lot of iterations of this. So let's look at a table of values. What does the square root of x over x, what does that graph look like? So if we make a table of values, I'm going to put in some negatives, 0, and some positives. So if I plug in a -2, on top I'm going to have a +2 over a -2. That's going to give me a -1. If I plug in -1, I get +1 over a -1. That also gives me a -1. At 0, I'm undefined. At 1, I'm going to have a 1 over 1. At 2, I'm going to have a 2 over 2, which is 1. So these graphs are always going to look, I just lost my, I'm not sure what happened. No. Okay, I'm not sure what just happened, and I'm hoping this is going to work smoothly, but I'll have to go back and check. So if I graph this, it means that at a +1, I have a hole because the graph is undefined at x equals 0, and anything above 1, I'm going to have a +1. Anything, this is at 1, and anything in the negative x is going to be a -1. So that would be what a graph of square root of x over x looks like. So notice if I were writing my limits, the limit as x approaches 0 from the left, that is going to equal a -1. The limit as x approaches 0 from the positive side is going to equal a +1, which means the two-sided limit does not exist because they don't match. You have to match from both sides. Okay, we're going to look at this now and do some algebraic problems. Okay, so we're going to be taking some limits. If there are no problems, you can just plug in the value. If there's a problem, then you have to maybe use a different strategy. So this first one says the limit as x approaches -3, x over x plus 3. If I try to just plug in -3, notice I get -3 on top, -3 plus 3. That would give me -3 over 0. So hopefully you realize you can't divide by 0. On the graph of this, that means I would have a vertical asymptote at x equals -3. What that means is the limit does not exist. Your graph is going to grow without bound whenever you have an asymptote. This next one, the limit as x approaches 4. So first I'm going to just plug in 4 minus 2 over 4 plus 4. There's no problem here. I get 2 over 8. So my limit, in other words, this is my input. My output would be 1/4. So that'll be my limit. In this next example, if I try to just plug in x equals 1, I would get 0 over 0. This is important. 0 over 0 does not equal 1. It does not equal 0. It's called indeterminate. So what you have to do is you have to do more strategies. You have to do more work. So notice I do have a difference of squares here. So what I'm going to do is factor this. On top I have x plus 1. On the bottom I have x plus 1 times x minus 1. So what happens is this cancels out, and now I can go ahead and plug in, whoops, it was a -1, sorry. There, that was a -1. So now I can go ahead and just plug in -1. So on top I have 1, On the bottom, I have -1 minus 1, so I have 1 over -2, and that's going to be my limit. So if you get indeterminate, 0 over 0, you just have to kind of keep going and find some other strategy to evaluate your limit. Now these next ones, these are your absolute value ones. Now notice I've multiplied everything by a -3. What that does is that's sort of like a vertical dilation. So what was before the -1 now becomes -1 times a -3 becomes 3. So this one now, this comes up here, and what was 1 before now becomes -3. So that branch goes down here. If you're not sure how the graph looks, by all means do what we did before and do a table of values, and it'll quickly come out what your graph will look like. Okay, so we can see that the limit as x is approaching 0 from the left, because that's from the negative side, is going to equal a +3. As it's approaching from the right, which is the positive side, it now equals a -3. When those two limits are not the same, the overall limit does not exist because it's not the same from both sides. Okay, now the last bit, we actually have already talked about this way back in chapter 4 when we talked about horizontal asymptotes. When you are finding a horizontal asymptote, you're looking at what is the graph doing when it goes off to infinity. So we have this concept of top heavy. That means that the power of your x on top is bigger than the power of the x on the bottom. So if I were to take the limit as x goes to infinity, it's kind of like saying what happens if I plug in really large x values. Since x is heavier on top, this is going to grow without bound. And so that means it goes off to infinity, which means there is no limit. The limit does not exist. Kind of like how it behaves when it's going to an asymptote. If it's bottom heavy, something like this, the limit as x goes to infinity. So if I plug in a really huge number for x, like 1,000, and then 1,000,000, basically this number is going to go to 0. And if you think about what the graph of 1 over x looks like, that is what is happening. As it goes out, the graph is getting closer and closer to the x-axis, so it's basically going to 0. So anytime you are bottom heavy, your graph goes to 0. And then this is the one that gave us our horizontal asymptote when you have the same power on the top. So if I had 3x plus 1 over, say, 2x minus 4, the limit as x goes to infinity, the only thing that matters, it's like plugging in really large values of x. The plus 1 and the minus 4 don't matter. The only thing that matters are those coefficients, and that would give us our limit. So in number 7, the limit as x goes to infinity, 2x over x plus 3. This is an example of having the same power. So you pick off the coefficient, so that limit is going to equal 2. In number 8, the limit as x goes to infinity of -x over x squared minus 1. Even if this is factorable, doesn't matter. You still have a higher power on the bottom. So it's bottom heavy, which means the bottom is going to grow bigger than the numerator, and it's basically going to go to 0. And this last one, x cubed over x minus 4, is top heavy. And so it is going to grow without bound, which means the limit does not exist. Okay? I know this is hard in a video, but hopefully this kind of made sense.